Now comes to the KDD Innovation Award. KDD Innovation Award is the highest award to the technical excellence in data mining. And this award is presented to one or a group of researchers making impactful and long-lasting contribution to the field. And this year, the committee is very pleased to anonymously recommend Professor George Karypis for this prestigious award. And let me say a few words about George. George is a distinguished McNair University professor and William Norris Chair in large-scale computing at the Department of Computer Science and Engineering at the University of Minnesota. At the same time, he is a senior principal scientist at AWS AI and ML. George probably is most known for his contributions to graph mining, graph partitioning, recommendation systems, and scalable AI machine learning algorithms. He will tell us more in his talk. Now, let's welcome Professor George Karypis to the stage. Congratulations.
Thank you. Okay, it's worth mark the X.
Okay, please stay.
Stay.
Okay. Now, as the convention of KDD conference, we welcome George to give us the KDD innovation talk. Thank you. Please.
Thank you. Stay away from direct light. So, good evening, everybody. So first of all, I would like to start my presentation with my closing slide, right? And the closing slide is a big thank you, right? So I'm very much honored and humbled by the award, right? I thank the committee, the award committee. I thank the nominators, and I thank the KDD community at large, right? So I was struggling the whole week, about how, what will be to include in my talk, right? So, and after literally spending a lot of time thinking Monday, Tuesday, Wednesday, what to do in my talk, right? I decided to say, well, kind of, center around to like 3 different themes, right? So one is to, highlight some of the work, over the years, right? To give credits to all the students, that actually did that work, right? Then spend some time talking about some of the things that I'm currently working on and I'm very much excited about. And then conclude the talk with some lessons that I learned along the way that have been very useful to my career. Okay? So, so I put together my slide deck, the initial draft of the slide deck on Thursday, Friday. I was not happy with that. So I was actually end up modifying until literally, early this morning. I was actually flew from Athens this morning. So I got up at 6 o'clock in the morning and I had a connecting flight to Rome. And then where I finished my slide and I mailed them and then flew over here, right? And I landed a couple hours ago. Right? So one of the things that you'll see in my slides, you'll see a lot of pictures. Those are, for those who know me, I have 2 hobbies, other than computer science, right? So one is taking pictures and the other one is hiking. And I tend to combine those 2 hobbies, right? And so all the pictures that you'll see in my slides are pictures that were taken actually very recently, and okay, so without, further ado, so, from you guys, heard, some of the reasons, why I was given that award. So it's a whole list of things about, high performance computing, graph mining, recommender systems, graph machine learning, and the applications. Okay. So, and what I would like to do is take each one of those kind of, areas and highlight some of the work and, highlight some of the students, that actually do their work. And by the way, this is a picture from Joshua Tree National Park. Anybody has been there? No, it's a great place. So, so in the high performance computing, So actually my thesis work was on high performance computing. I'm not a data mining person. My kind of, first love, so to speak, on the science side has been the high performance computing area. And that was a work that we continue, as a lab doing, after, I became a faculty, right? And there's a lot of the work that we did over there around, graph partitioning, around, parallel solvers, around, scalable ways to do tensor factorization and so forth, right? And this is work done by, my students, back then, Kirk, Shaden, Jeremy, Irene, and Dominic. In some of the recent years, right, and again, and many of you guys may be probably familiar with things like MIDIS, PAR-MIDIS, and H-MIDIS, right? The thing that surprises me is that, those tools are still used extensively today, some 15 plus years, since those things were written. So there's something to be said about writing code in C versus Python, right? So now, some of the most recent work on the high-performance computing side has been around on enabling a lot of modern machine learning workloads. And this is a lot of the work that was done with my colleagues at Amazon, Da, Xiang, and Shuai. And there's a lot of work over there that we've done in the last 6 or so years on how do we scale the training of large GNN models. Right, and both for and also how to enable the training of temporal GNN models, as well as how do we train scaling of large language models, right? And developing distributed training approaches that work well on large number of GPUs. So the second area in which I spent a lot of time in my career working on is the area of graph mining. And Japie already mentioned some of that stuff, but when I started my career, I was fortunate to recruit some very bright students that really started the field of graph mining, right? So that was the era back of early 2000, right, in which they actually developed the graph algorithms to find frequent subgraphs. Right, and both exact and approximates, right? And this is a work that over the years have won several test of time awards, and also as well as both patterns in time evolving graphs, as well as geometric graphs from being able to find pharmacophores and other things that are relevant to protein structural bioinformatics. And then that work on, the graph mining work also kind of moved on the graph-based clustering work as well as, graph analytics work, right? And there was a set of students that worked to actually develop things like very effective ways to find all the k-nearest neighbors in the graph in an exact as well as approximate ways. So those are, computationally efficient algorithms, as well as algorithms to be able to quickly enumerate the triangles in the graph, do a k-trust decomposition and other key graph analytics operations. So the data area in which, I have spent a lot of time with and have been fortunate to work with a lot of students on that is on recommender systems, right? So, early in my career, I, got introduced to the fields of recommender systems. And, from my affiliations, I'm from the University of Minnesota, right? The University of Minnesota is one of the places that, recommender systems have started, right? A shameless publicity kind of announcement. So next year we have the 25th anniversary of, of Rexis happening in Minneapolis, right? So you guys are welcome to come. So that was the early work of item-based recommender systems, right? And also the early work on SVD-based ways of doing recommendations. It's kind of funny on the item-based recommender system. For those guys who are familiar with the history, there was an academic war was happening, that Minnesota, in parallel with commercial work happening in Amazon at the same time, right? And those things, pretty much, happen in parallel. Right? And of course, being Amazon, right, and Amazon could not publish any of that work, right? So a lot of that work became associated with the University of Minnesota, even though, similar work was done at Amazon, behind the scenes. It's also funny that now I'm affiliated with Amazon, so I get to actually, talk to work with those people as well. So, and then about 15 years or so ago, right, so that was some of the early work on recommended systems. Then the whole line of work was created by some work that Xia Ning started, which I can see her sitting over there, on developing a SLIM, which is a sparse linear models for recommended systems. So that was one of the early approaches to actually use a structural correction model to learn item-to-item similarity metrics to be able to derive item recommended systems. Okay? And that work led to a whole slew of other related research in the field of recommended systems and methods that they are still actively used today. Right? And then about 6 or 7 years ago, actually no, that's not correct, about 8 years or so ago, right, so we started a big effort around educational data mining, in which I was fortunate to work with a set of students that actually developed recommended methods specifically tailored for educational domain, right? For things like how to identify the right courses to recommend to a student, how to come up with a degree plan, and things of this nature. Okay. So, and the last topic on those things over there is the graph machine learning, and graph machine learning is something that I was initially involved, not very actively, but became one of my focus areas, as soon as I joined AWS. And I was fortunate to work with a great group of colleagues over there on developing some of the early graph machine learning systems, right? Both for academic as well as industrial use case. So many of you guys may be familiar with DGL, the Deep Graph Library. So this is something that, that was developed by my team at AWS. And it's a widely used, framework for training, graph neural networks. At the same time, we developed something called GraphStorm, which is also an open source tool that is designed to solve graph machine learning problems at enterprise scale. So this is a type of, graph machine learning toolkits that they're a low-code kind of tool, right? That makes it easy for people to actually, train and deploy graph neural network models in production. And a lot of that work also was powered with a lot of systems level work that was done to be able to enable the training of those models. And also there's been a lot of work that we've been doing in terms of, how to do question answer over graphs, and most recently how to combine GNNs and RAG together to be able to combine knowledge bases with RAG. So this is kind of a spectrum of work, right, that happened in the last 20 plus years, and would not have been possible if it was not all the students involved in that work. Right? But I was also fortunate to also collaborate with some senior researchers, right, and I'm sure this is a very selective list, right, and I'm sure I have missed a lot of people. And some of those faces probably do not need an introduction, right? So I mean, everybody knows Christos, right? Everybody knows Vipin, everybody knows Alex. Alex, was actually the guy that recruited me to AWS, and worked together for several years. Many of you may know John Riddle, right? So John is the second person on the first row, right? John was instrumental in getting me hooked into recommender systems. Right, so, and then Wei-Shu Hu, which is the third person on the first row, as well as Ella Tadmore, which is the first person on the second row, my colleagues in biology and material science domain. They have been very good mentors and teachers in that field, right, for a lot of the work we're doing. Plus, Nikos, which is an expert on tensor methods, and Zizi, who is my partner in crime in a lot of the GNN work, out of Shanghai. Okay? So, whatever. So let me spend a couple minutes talking about, what are the areas that I'm focusing right now. So the thing that, I spent a lot of time and is around, foundational models for less traditional domains. And again, foundational models, have taken over the world, right? So this is something that used extensively across different areas. I mean, most of the success has been in text and images and audio and video. But we're seeing also a lot of success, we're starting to see success in non-traditional domains, right? So one of the areas that we've been seeing the rapid advancements of foundational models is around, time series prediction. So my team at AWS is responsible for building the Kronos time series models. I don't know how many of you guys are familiar with Kronos, right? But one of the little known facts is Kronos models have been downloaded over 500 million times from Hugging Face. And I'm still baffled, what are people doing with the Kronos models, right? So, my hypothesis is they use it for some sort of a stock market, stock price, prediction kind of task, okay? Again, this is an area that is a very active area of research in which, we can actually do very accurate time series prediction and actually can do a zero-shot time series prediction. Another area that is non-traditional on the foundational models is around foundational models for tabular machine learning tasks, right? So we recently released a set of models called Mitra, which is the lower right picture over there. So this is part of the AutoGluon. It's an open source, AutoML toolkit that we have that achieves, state-of-the-art performance in predictive tasks, right? And again, for those who are not familiar with what those tabular foundational models are the type of models in which, you give it essentially your variables and says predict X, and it will give you a prediction as part of actually doing a forward pass on the model, right? And those are the models that they are trained on a lot of large synthetically generated data and be able to have, zero-shot, prediction performance and actually perform extremely well, right? And on the academic side, also on the AWS side, we're also working on foundational models for a lot of the data analytics tasks. And it has to do with things about entity linking, about to be able to do, text to SQL and things of this nature, right? And then on my academic career, very much spending a lot of time with my colleagues at the University of Minnesota, as well as at NYU, on foundational models for material science, right? So this is another area in which, we've been seeing success in building those foundational models. So now the good thing about that stuff, especially, both the academic as well as the stuff we're doing in AWS, is the models are actually, the weights are publicly available. So all of those things are on Hugging Face, and you guys can go and download them and, and experiment with them. Now the second area in which I spend a lot of time, right, is what we call systems for Gen AI and Gen AI for systems. Okay, so I mean, all of us are familiar with the rise of the large models, right, and the cost associated with them, right? So the cost of both training those models and the challenges associated with that, as well as the cost of actually doing inference of the models. In my mental model, training is a one-time cost. Inference is a forever cost, right? So, and what we need to be doing is to be able to optimize our systems to do both, enable and support large-scale training, and also being able to do low-cost inference. And we're doing a lot of work within, my team on how to optimize that stuff. The unfortunate part is that those are certain things that, we tend not to be very open about, publishing that stuff. Right, so that's the unfortunate part. That's another one area in which I spend a lot of my time. This is on the system for Gen AI, right? But the other part that I'm very excited is the whole idea of Gen AI for systems, right? And the idea there is to leverage Gen AI to improve the systems that we build to train models, to do inference on those models and so forth. And so we have a project that we started about, earlier this year on building generative models and RL-based models to optimize kernels for our custom silicon at AWS. So AWS, it has its own custom silicon. It's called Trainium chips. And the Trainium chips are programmed on a language that is called a Neural Kernel Interface, NKI. We call it NIKI. Right? And NIKI is nothing like, it's a Pythonic language. It's nothing like CUDA or anything like that. And of course, every time you introduce a new language, right, a new SDK, there's a steep learning curve, right, for people to be able to use it. So one of the things that I want to do is to be able to develop, Gen AI tools to actually automate the development of efficient kernels, right? And for obvious reasons, right? So we can take those things and do drop-in replacements on what comes in from a compiler, to get better results and so forth. And we've been experimenting with inference time compute approaches to optimize kernels, right? And here's the three figures over there that show the gains that we get as a function of the trial, right? In terms of the performance that we get. Okay, so this is an example of leveraging Gen AI to optimize the systems that we use for Gen AI, right? And the same thing can be done for other things beyond kernels, right? You can do the same for communication libraries. You can do the same thing for sharding strategies. You can do the same thing for how you build your fault resilience infrastructure and everything related to that, right? So this is another area in which I spend a lot of my time. And I would like to kind of wrap up by kind of 3 slides. That kind of, what did I learn along the way, right? I was kind of, thinking about the Innovator Award and the Senior Citizen Award, right? So I guess I fall into the Senior Citizen Award type of category, right? So obviously I must have learned something over the time, right? So, by the way, this is a great picture of, anybody knows where the picture is from? Arches. No, you don't think, you thought you knew, but it's not from there. So one of the things that I have learned is the random walk does not work in research. So you should not be doing research by doing random walk, right? So you should establish your priors, right? In terms of, I have, some hypothesis, right? I have a mental model of how things should be. Right? And then, design your experiments, do your analysis, do your research, right? And if your results do not align with your mental model, look for bugs on either side of the whole thing, right? So the other part is very important to be able to dive deep and be hands-on, right? Because, at the end of the day, as a researcher, right, even, you play the role of a faculty and a student and so forth, or you should be able to help your student, to resolve issues, right? So this is something that even as you get grayer or hairless, right, you should not be, moving away from being able to dive deep and be hands-on, right? So this is very important, and I found it critical to actually succeed. So the second part is to understand the domain that you're working on, right? And learn from what came before you. By the way, my youngest son wants a Vespa. So that's why. So I found a picture of Vespa for him. Yeah. So one of the things that I have found over the years is that you need to be able to especially if you get to a new domain, right, you need to spend a lot of time first understanding the domain, right? And this is where having great collaborators in that domain are critical, right? Because those are the people that you go and essentially pick their brain and their mind to get the insights, right? And then the other part that, we need to do is to be very respectful in terms of what the scientists in that domain or scientists before you were able to do and learn from them, okay? Sometimes I see something that, well, I have a big hammer called a deep neural network. I'm going to throw it in the domain, right? Good stuff will come out on the other side. It almost never works, right? So, and however, deep neural networks is a powerful tool, right? But if you understand the domain and you respect what came before it, right, you can take advantage of that. And the last part is actually the hardest one, is what's called knowing when to press on and when to move on. Okay, so this is a nice picture going up Mount Olympus in Greece. So what do I mean by that, right? So pressing on meaning is persevering, right? You know, keep on working on the problem, right? I mean, not give up, right away. But of course, there's a flip side to it, right? If you can keep on working on the same problem again, without making any progress, right? Then maybe it's time to give up, right? And move on to something else, right? And knowing when to press on and when to move on, right? Is something, of course, you know, you learn through experience, right? But this is very important. And one of the things that I have learned in my career is that sometimes when I hit a dead end in a particular area, it's perfectly fine to say, I'll take a break for a few years and come back again, right? And I think this is very important and an important lesson. Okay, so I think my time is way up because the timer went down to 0 a long time ago. So again, thank you. So this is a picture that I took a week ago. And if you like the color version of the picture, it looks like that, right? So again, thank you very much.